Good day. For those of you who do not know me, my name is Douglas Harder, and in this topic we're going to look at the adaptive Euler-Heun method. So in this topic, we will derive the adaptive Euler-Heun technique from the methods described previously on adaptive algorithms. We will look at the implementation, and we will see two examples. All right, let's go over the adaptive Euler-Heun method. Well, given the point t sub k, y sub k, we will calculate both the slopes s0 and s1. We then have two approximations. Our suboptimal approximation is Euler's method, and that we will assign to y. Our more precise estimate is from Heun's method. We will assign that to z. Now, our approximation of the error of Euler's method will now be twice the difference between these two approximations. Because, after all, if Euler is significantly worse than Heun's method, then the difference between Euler and Heun is probably pretty close to the distance between Euler's approximation and the actual solution. However, just to make sure, we're going to multiply that difference by 2. Consequently, we will overestimate, or at least we intend to overestimate, the error of Euler's method. Now, from our error analysis, we know that one step of Euler's method is order h squared. Therefore, the error we just estimated, twice the difference between z and y, will be approximately c times h squared, where c is of course an unknown coefficient. However, we can approximate c by solving for it, and therefore c is this calculated error over h squared. Now, we don't want to use this interval width size. We actually want to find the ideal interval size a times h so that the error is the absolute epsilon value times the width of this new interval. All right, so we want to solve this equation here. Now, one of the ah's cancels from the left-hand side, and therefore we can solve this for a. Specifically, we just divide the left-hand side by a times h, or c times h, and we have that expression there. However, from above we have an estimation of c, and so we can substitute that back in, and therefore, theoretically speaking, this is the ideal interval width, this a times the value of h. That's the interval width we should have been using at this step. Now, if a is less than 1, then we should have actually been using a smaller step size. So we'll have to recalculate because our error is too large. However, if a is greater than 1, then we were using too small a step size, and therefore this suggests that we should be using a larger step size with the next step. All right, adding this to our implementation is actually quite straightforward. We're going to calculate the initial slope, which is already stored. It's the most recent calculated slope, the slope at the most recent point, and then we will estimate the value at the next point using Euler's method. The most recent value of y plus h times the slope we have there. We will then calculate the slope at this new point. So the most recent value of t plus h evaluated at this point y. We will then find Heun's approximation, which is the last value of y, plus h times the average of these two slopes, and that is Heun's approximation. We can now estimate the value of a, and if a is greater than 1 or h is already too small, so small that we can't make it any more small, then we're going to use this value, and so we update the three q's. Finally, to actually update h, we will not update h by a times h, but rather we will multiply a by 0.9. So that guarantees, or almost essentially guarantees, that with the next iteration, h will be close to optimally large, but not perfectly optimally large, meaning we're almost certainly not going to have to recalculate at the next step. Unless, of course, there's a discontinuity. Now let's look at one example. Here we have our initial value problem that we've seen a few times before. Let us call this adaptive Euler-Heun method with a minimum h value of 0.01 and a maximum h value or step size of 1. The absolute epsilon will be 0.1. Here's the output. Notice that wherever the function is reasonably flat, the h size becomes very large, but where the function starts to curve, the h size gets much smaller. That is because if the solution is flat, then we can follow the slope for a significant distance while still maintaining accuracy. Whereas if the function is, or the solution is changing rapidly, we need smaller step sizes so that the following the slope actually gives us still a reasonable approximation. Now, nowhere here do we hit the minimum step size, and nowhere here do we hit the maximum step size. But you can see how the step size is changing as appropriate. Suppose, however, we have a decaying exponential plus a discontinuous forcing function. So this forcing function is only turned on after t is equal to 1. What that means is the solution is no longer going to be differentiable at that point. And you should have seen that in calculus. Let's see how adaptive Euler-Heun deals with this. Well, once again, with the same limits, we have the following approximation. So notice again, initially, the slope, the rate of change is almost nothing. It's almost a flat line. So therefore, h is doubling in size. First it's 0.1, then it's 0.2, then it's 0.4. But then it starts shrinking again. And right at the point of discontinuity, h is actually reduced down to the minimum step size, because these algorithms, Taylor series, assume that these functions are continuous and differentiable. But this one is not differentiable. And so therefore, to get the necessary accuracy, h has to be arbitrarily small. However, we've put a lower bound on the size of h. Okay. And so we still get a reasonable approximation. Notice after that, the step size is essentially doubling with each subsequent step, because again, remember, the maximum we allow the step size to change is by a factor of 2. Then when the function starts to curve again, the step size gets smaller again. All right, so hopefully these two examples show you how adaptive techniques can work, and hopefully this particular example of Euler-Heun demonstrates how the approximations using Euler and Heun can be used to estimate the error of the weaker one. And it seems to work. Following this topic, you understand the adaptive Euler-Heun method and are aware of its derivation. You've seen the implementation of this method, and you've seen two examples. And specifically in those examples, you have seen how the step size can be made smaller or larger as necessary so as to keep the approximation within the bounds required. Of course, we're using Heun's approximation in the end, but we are estimating the error by looking at how good Euler's approximation is. And consequently, the results are quite pleasing, even if the absolute epsilon size is quite large. Here are the references, acknowledgements, the colophon, and a disclaimer. Cheers!